So I wanted to record this lecture because I felt like we went through enzymes a little fast. I want you to really understand what an enzyme is because they are so important in all biological reactions. So this is showing an enzyme catalyzing. So enzymes are a catalyst, which means something that speeds up a reaction. So in this case, the enzyme is in gray, and the enzyme is binding a substrate, which is the molecule or molecules it's going to work on. And the substrate fits into the active site. So the active site of the enzyme is where the reaction is going to happen. And we've talked about the lock and key idea that just describes that enzymes and substrates have a very specific interaction. And you can see that shown by how it fits right into this groove here. The enzyme and the substrate make a complex. The enzyme then makes products, and the products are released. So one of the concepts we talked about in class is that enzymes can be reused. Okay. So the substrate binds the enzyme, the chemical reaction happens, and then the products are released. This type of reaction is called catabolic because you are taking a substrate and breaking it down. Catabolic reactions release energy. Catabolic reactions are also called exergonic. So just from this very simple figure, you can learn a lot about enzymes. So let's look into all of this a little bit more. A term you need to understand is free energy, which is represented as G, also called Gibbs free energy, named after the scientist. And the change in free energy, which is delta G, as it says here, determines the direction of chemical reactions. Okay, so it determines if a chemical reaction is going to happen on its own or if it needs help. So that's what we're going to talk about with these exergonic and endergonic reaction graphs. So the first type of reaction we'll talk about is exergonic. The delta G is negative, energy is released, and it's called spontaneous. So that means it will happen without having to add energy. When you have an exergonic reaction, the energy in the products, that's not right. The energy in the reactants is greater than the energy in the products. And I represent energy just as this capital E. Right? That means you've got to have the rest of the energy go somewhere, and that energy is released, and a lot of times our cells will harvest that energy to do other reactions, and that's called energy coupling. Okay? So the reactants have a lot of energy, the products have less, the energy is released, and remember to calculate delta G. You take the energy of the products minus the energy of the reactants. And so on this graph, it's showing how the reaction is happening, or as the reaction is happening, the level of free energy. And remember, you can just put any kind of values here you want, right? So you could put this as a value of 10. You could put this as a value of 50, right? It has to be more because it's higher on the graph. And so if you plug it into the formula, the energy of the products is 10 minus the energy of the reactants, which is 50. Your delta G is negative. Energy is released. Okay. The delta G shown right here is the difference between the products and the reactants. Oops. The opposite type of reaction is an endergonic reaction. And what I want you to see on the graph here is that you have to put energy into this reaction. It cannot happen on its own. It's not spontaneous. The delta G is positive because if we put the same values of 10 and 50 at these lines, and we said the value of products is 50 minus the value of reactants is 10, you get a positive, delta G. That means you've got to put energy in to make this happen. This is an anabolic reaction. It means you're building something. So I'm writing building macromolecule. So you're building a big molecule. And that makes sense that it takes energy. It's harder to build something than to break something down. Okay, so where do we get this energy if we need it to make a reaction happen? Well, ATP, which stands for adenosine triphosphate, which is an RNA nucleotide. We haven't talked about these molecules yet, but they have this structure with 3 phosphates, a sugar, and this base. Okay, so RNA is very similar to DNA. So nucleotides make up both RNA and DNA. We'll get into this next unit. As you can see in the video here, when you break this bond, you release energy. So breaking down ATP, and remember when you guys drew pumps, you said it needed ATP, and some of you even wrote ATP to ADP plus P or PI, which is correct. The D stands for diphosphate. So you can see ATP has 3 phosphates. What's left has 2 phosphates. And that little phosphate there has energy because of this bond that gets broken. And what you're going to see in these chemical reactions is we can transfer this energy in the bond to another molecule. So, excuse me, this diagram is just showing that when you hydrolyze, when you break down ATP, you release energy. And when you want to make ATP, it takes, I don't know why this pen does this. It takes energy. And this is what we're going to talk about next with cellular respiration. So ATP, in our cells is continuously being broken down and remade. Sorry. This is just showing the same thing. Hydrolysis, the breaking of that ATP phosphate bond. And now we're putting some numbers with it. Delta G is negative, so it's an exergonic reaction. It releases energy. So the goal of your cell is to grab that energy to drive other cellular processes. And grabbing that energy is called energy coupling. So this endergonic reaction, which you could also call it anabolic, right? Because we're taking two components and putting them together, we're building something, has a positive delta G. It needs, let's see, I'm right, this reaction needs energy. It needs at least 3.4 kcals per mole to happen. So where are we going to get that energy from? We're going to get it from the breakdown of ATP. So now we make this reaction happen in two steps. And first, the glutamic acid and ATP come together, and where they come together is in an enzyme. Okay, so none of this is happening just in the cytoplasm, in the cytosol, just magic, right? It's happening in an enzyme. An enzyme is making these reactions or helping these reactions happen. So what happens is we break down ATP, we give that little energy phosphate to glutamic acid, and we have ADP left. So it's just this reaction, but now the phosphate is attached to another molecule so that that molecule has some energy to go on and do another reaction. And so the phosphorylated glutamic acid now has a little bit of energy, and it can form a bond with ammonia, and now we've created the product that we want. The phosphate is released. In the mitochondria, these two can come back together and make ATP. And if you looked at the values, you would see that this reaction to make glutamine requires 3.4 kcals. The reaction just to break down ATP, like I showed you here, releases 7.3 kcals. And so overall, you have a net negative 3.9 kcals. So coupling these reactions tells you, yes, you can actually make this happen. It can't happen on its own. It can only happen when we couple it to the hydrolysis of ATP. So energy coupling is taking two reactions and putting them together so that you can use the energy released from one to make the other one that needs energy happen. Okay, so again, delta G is the difference between the energy in the products and the reactants. But there's actually a little bit more energy that's needed. So a more accurate energy diagram, and what I'm going to show you, let me see this, this is the same thing we were just looking at. Okay. Same bar graph. reactants. Oh, I want to make it. Right. And products. It's very strange. Okay. Bar graph just like this. Let me move my pen back. Pen. Okay. So all we're doing is we're doing this hump because there's really this little extra oomph that you need to make a chemical reaction happen. Okay. And that's true for exergonic or an endergonic. Right? So here's the reactants, here's the products, and now above our highest energy point here, we have this little oomph. What's important to see is that the delta G, which is the difference between the products and the reactants, doesn't change, even with this little hump. Okay, delta G stays the same. It's always the difference between the products minus the reactants. What this hump is called is the activation energy. So you'll see it EA, you sometimes see it EA, you can see it E with a little a subscript. Activation energy is the additional energy needed to make and break bonds. So this is the energy stored in the reactants, this is the energy stored in the products, and this is the extra oomph needed to be able to convert the reactants to the products. Again, you can think about this as going up this hill. It takes this little extra oomph to get down, or on a swing. Right? You can either pump your legs and get swinging, or you can have someone push you, and that's going to work easier for you. And this push person is acting like an enzyme. Right? So if you got some more people to help you, or maybe you got a rope to pull it up, anything that makes it easier to go over this hump, that is what an enzyme does. And there's a little YouTube video that you can watch.
For any reaction to occur, even one that releases energy, some energy must be added to get the reaction going.
So
this energy is needed to break bonds. The energy needed.
So again, the enzyme effect is to lower the activation energy. So when you guys were drawing your graphs, for some of you in your homework or your pre-class assignment, what I want you to see is be careful when you draw it, right? The reactants energy stays the same, the product energy at the end is the same. What's lowering is this activation energy. So as we measure, right, the free energy is still product minus reactant, this thing right here. The activation energy is the energy from reactants to the top of this little peak. Okay, which technically is called the transition state. And what that means is that in an enzyme, as you're trying to, here's ATP and here's glucose, as you're trying to transfer a phosphate onto glucose from ATP, so as you're trying to break down ATP and transfer that energy to glucose, it takes a little bit of manipulation, right? You've got to strain these bonds and you've got to remake these bonds. Okay, think about like if you played with Legos or Tinker Toys or anything that you were building, right? Sometimes to take something apart and put it on somewhere else takes a little bit of extra energy. That's what this transition state is, and that's what enzymes are good at doing, right? They lower the activation energy. They lower this hump because they're making it easier by putting these molecules together in the right environment. They're making it easier to happen. This would be like someone handing you your Legos so you could keep building versus you having to get up and go find the ones that you need. Right? Makes it easier when you get some help. So, the enzyme effect in the activation energy, again, oh, that's interesting, is the energy from the reactants to the top of the peak. So, uncatalyzed means no enzyme. Right? So reactants to the top of this peak, and when it's catalyzed means plus enzyme. The activation energy is less. Same thing over here with an endergonic reaction. You start at the reactants and you go to the top of the peaks. So without an enzyme, the activation energy is greater than with an enzyme. Delta G stays the same. Delta G doesn't change whether you have an enzyme or not. Big important concepts. Okay, so we've kind of talked about an enzyme. Most enzymes are proteins. Proteins are made of amino acids. Remember that enzymes have this active site, this groove where the chemical reactions happen. Their whole job is to bring molecules together so that the reaction can happen faster. And they are a catalyst, or they catalyze. I'm trying to think of. Okay, so they speed up reactions. So enzymes make and break bonds. You can have a catabolic reaction where you're breaking molecules down. So you have a big molecule and you're breaking it into two. Right? This is going to release energy. This is going to be exergonic. Okay. This one is going to have a negative delta G. Releases energy. This one shown here, you're bringing two substrates in and you're making a product. So you're building a new, bigger molecule. This is called, I can't spell, this is called anabolic. Okay. The delta G is positive because this kind of reaction requires, I'm really having issues. Requires energy. So it's anabolic, it's building a larger macromolecule. Cannot happen on its own, it's not spontaneous. Well, actually, none of these reactions happen on their own, they all require enzymes. Exergonic are considered spontaneous. Right. building a molecule, anabolic, positive delta G. Those are basically your two types of reactions, either catabolic, breaking something down, or anabolic, building something up. This diagram is just to remind you that enzymes are reused. All right? So the substrate enters the active site. The enzyme changes shape. This is called induced fit. So lock and key tells you it's specific. Induced fit, you can see the difference between this enzyme, and this enzyme, right? They're slightly different shapes. So just like when you're hugging your dog or your cat or your boyfriend or girlfriend or mom or dad or brother or sister, right? Your active site, your hug, changes shape. Okay? Changes shape when you bind to that thing you're hugging. Okay? That's induced fit. Okay? It's saying substrates held in active site by weak interactions. So it's a stable interaction. The enzyme converts the substrates to products. The products are released. The enzyme is now able to be used again. This is another diagram showing induced fit. Here's the active site. It is specific for the substrate, but upon binding the substrate, the molecule closes in on it. The fit is induced. So now it's all hugged snug in there. Last concept, enzymes are affected by the environment, and we haven't talked about these enzyme molecules yet, but they're made of amino acids, and they're a long chain of amino acids, and they fold into a very specific shape. Okay, so they fold into a specific shape, right? So you can see this has a very specific shape. It's not a long string anymore. Now it's folded up into a shape that has this active site that allows the substrate to bind. Okay. The shape is essential for function. If you ruin the shape, you ruin the function. So this diagram, the purple line, is representing this long chain of amino acids that's folded into a shape, and that this shape is held together by chemistry, by bonds. If you disrupt those bonds, you disrupt the shape. So things that can disrupt bonds are temperature. Temperature adds energy, and as these things get more energy, some of these bonds will break, and the protein can unfold and lose its shape. The other thing that affects bonds is pH, acid and base. Those also interfere with the bonds and can make a protein lose its shape. So this is shown here. Each enzyme has an ideal environment. So in this case, an ideal temperature and an ideal pH. So most enzymes in our body work the best at 37 degrees Celsius. That's body temperature. And what this is showing is a rate of a chemical reaction. So at the lower temperatures, it's very slow. Right? The reaction is not happening. The enzyme's not in its ideal environment. When we reach around 37, the reaction is happening at max speed. The enzyme's working as efficiently as it can. As you increase the temperature, again, you lose the activity of the enzyme because you're messing with its shape. So as I mentioned, we take advantage of this when we're working with food, right? We put food at cold temperatures, really actually here, 4 degrees Celsius is your refrigerator, to slow down any chemical reactions so that your food doesn't spoil. So there's bacteria everywhere. There's mold, fungi everywhere. Right? So what you're putting it in the fridge is to slow down all those chemical reactions by whatever might be contaminating your food so that it can't grow into big numbers and make you sick. The flip side, you can cook your food, right? You can heat things up to high temperatures, and that's killing any of those little microbes because it's breaking down all of their enzymes so that they can't grow and make you sick. pH, acid base. Right? So hopefully you had a little exposure to some chemistry. You might have worked with acids. Vinegar is a household acid. Smell it, it like kind of burns your nose a little bit, especially if you like to eat those hot wings. Ooh, when people have hot wings at a restaurant, I can smell that vinegar. Right? You might have bleach at your house. Bleach is a base, right? It's slimy. I wouldn't suggest you go touch these things because they will ruin your skin, but, well, not vinegar, but definitely concentrated bleach is not good for you. Some of the, like liquid Drano and things like that, use acids or bases to help break things down. So acids and bases are really good at breaking things down. These are names of different enzymes. And all this is trying to show you is each enzyme has an ideal temperature and pH. So chymotrypsin likes a semi-neutral pH, pH 8. Pepsin, which is in your stomach for digestion, works at a very low pH, very acidic, pH of 2. That's what's in your stomach. That's why people who throw up a lot will start to ruin their teeth and can get blisters inside their mouth because all of that acid, and it hurts their esophagus, all that acid is coming up from the stomach where it's to places it's not supposed to be. It's not supposed to be up in your esophagus and your mouth. And that acid can break down proteins and can cause destruction of tissue, so your cells. Some enzymes work at any pH. Okay. Some enzymes are really active at higher pHs, which is base. So the take-home message is that enzymes are affected by the environment, and each enzyme has its own ideal temperature and pH. Most enzymes in the body work at 37 degrees, that's body temperature, but for microorganisms like bacteria and fungi, they can work at lower temperatures as well. The last concept that we didn't get to is the idea of saturation. So remember we mentioned a little bit about carrier proteins for transport, and that they can get saturated, they can get maxed out, where they're working as fast as they can to move things across the membrane, right? But there's only so many of them, and so you get this buildup of substrate, for instance. Same thing with an enzyme. Okay? Here's lots of enzyme, little substrate, right? And it's working fast. The rate of the reaction is going, it's going fast, and then at some point you have too much substrate and not enough enzyme. and the enzyme can get maxed out. It's going as fast as it can. And so what you see with the reaction rate is it just levels off. It can't keep increasing because you don't have enough enzyme to keep reacting with the substrates. So that's the idea of saturation and why enzyme rates, how fast the reaction's going, are affected by substrate concentrations. They can just max out. So our little summary slide, metabolism is the combination of your catabolic and anabolic pathways. Your catabolic are your breakdown, your release of energy, your exergonic, negative delta G reactions. Anabolic are your building of molecules, requires energy. It's endergonic, and you have a positive delta G. All right, don't forget, whoops, you have a bunch of clickers.